All right, perfect. Hello, everybody, and welcome to the Math Behind Machine Learning workshop. My name is Mohit B, and I am the Director of Website Development at C4C. So, what I would like to say before we actually start is that this workshop is a part one of two, because the second part is the actual machine learning itself, and that is taught by another member of C4C. So let's get right into it. So why do we need to learn math for machine learning? So as technology has progressed, as we've got more intricate coding languages like Python, they allow us to actually compute all of these numbers well really efficiently. In fact, if a particular solution or a problem would take us around 5 minutes to solve, whereas it would take a computer, well, a lot less to solve, right? Because it's a computer. So yeah, you won't need to like do any written math as such, but you should understand what's actually going on in the back end for the math part of it at least. And you will also need to understand the math behind many concepts of machine learning, which will be covered soon, as I previously mentioned about the part of the workshop. So in conclusion, let me allow me to express my love for mathematics and extend it to you. So what will be covered in today's workshop? We're looking at linear algebra, multivariate calculus, probability, and statistics. Now, there are there's a lot of depth in these four topics that I've just mentioned. In fact, a lot of it will not be covered in today's course, mainly because of the fact that it's really complicated to understand over a online means. So keep in mind that there's still a lot to learn. This is almost the surface level, right? You're just dipping your hands into the water. And additionally, by multivariate calculus, I mean differentiation or multivariate calculus. So let's start off with linear algebra in specific scalars. Scalars are basically a value that represents something. Now, this representation could be anything. It could be the size of a football pitch, a price of a laptop, maybe the number of people we have in this meeting right now. It could be absolutely anything. And the best part about scalars is that you can actually carry out arithmetic operations on these scalars. So arithmetic operations include addition, subtraction, multiplication, and division. Let's look at a very simple example. Let's say that the price of property in Dubai is $2,000, and you're getting 50% discount on it because you have some sort of coupon code, some sort of contact, and this price will actually fall down to $1,000 because basically we're dividing $2,000 by 2, which is 50% of 2,000. So yeah, that basically showcases the division as an arithmetic operation on a scalar. Now let's get into vectors. So we can interpret vectors as a list or numbers that represent something, and we often tabulate data into these different forms. So by forms, I mean you tabulate this data into like rows and columns, as seen in matrices, and we'll actually get to those. And the very cool thing about vectors is that if you're presented with an image which has pixel data, we can actually transform those pixels into matrices. And what that would allow us to do is perform operations on them. As you learn more about machine learning and artificial intelligence, you'll come across this specific type of neural network. It's completely all right if you don't know what neural networks are, known as a convolutional neural network, which will allow you to carry out operations on these images. So that's why we need vectors. So as I previously mentioned, you can perform arithmetic operations on vectors. So let's look at vector addition. Let's say I have this vector v1, which holds the value a, and I have this vector v2, which holds the value of half a. Well, because this is half the magnitude of v1. Not exactly, but let's just assume that it's half of the magnitude of v1. So what we see is v3, which is this which is this vector, would be equal to the magnitude of vector v1, which is a, plus half a, because that's the magnitude of v2. So what we end up with is 1.5a. That's, in simple terms, vector addition. Next, we have scalar multiplication on these vectors. So again, let's consider a vector a, and if we multiply that vector by 2, that would increase all of its values by a factor of 2, right? By a scale of 2. So as we can see, this is twice the magnitude of a, right? That makes sense. Now we look at vector projection. Now let's just consider we have two vectors. Consider these two vectors, and let's just say that we know a lot of information about vector v2, right? We know practically everything about it, the direction, the magnitude, anything that it has to follow with, right? But we know very little or absolutely minimum about v1, which is the first vector. What we can do is actually project this vector onto v2. And what this projection will allow us to do is find out the details of vector 1. Now, where is this used in machine learning? Especially in pixel data or images. These projections can actually help us find the shadows of a pixel. And by shadows, I mean literal shadows, which are caused by light, right? Let's get into matrices. Consider we have two equations. 4x minus 2y is equal to 4. That's our first equation. And 5x plus 3y is equal to 16. Now, if you were to represent this in matrix form, well, you would represent it as like this. 4 minus 2 comes from the first equation, and 5 and 3 come from the second equation. Right? So always make sure that you have your first equation in the first line of the matrix, and you have your second equation in the second line of the matrix in the same order as it's given in. And well, you have x and y, which are two constants, which we can find using simultaneous equations. Let's not get into that right now, though. But yeah, what you have to do is put x and y as columns in this matrix, and we know that these particular values, well, when you multiply them, will come out as 4 and 16, right? So yes, we can actually solve this matrix if you like combine it together. So using row echelon method and the inverse row method, but those are two really complicated things and we won't really get into that. But an additional method of solving this equation is by method of elimination. So method of elimination, basically what we have to do is, well, I think someone left us, but that's all right, is convert all the positive signs to negative signs. So negative 5x minus 3y is equal to negative 16. Therefore, we can, well, what we can do is find out that y is equal to 2 and x is equal to 2 as well. And let's actually try plugging that back into the equation to see if our solution was correct. So 4 into 2 is 8, 2 into 2 is 4, 8 minus 4 is 4, so that's correct. 10, because 5 into 2 is 10, and 3 into 2 is 6. So what we get is 10 plus 6, which is 16. So our solutions are correct. Now let's get into matrix addition. This is a really simple concept. All you have to do is take this value and multiply it by the corresponding value of the other matrix, of the second matrix, right? So what you get is the top left of this matrix plus the top left of this matrix gives us 4 plus 1, which is 5. Let's look at this one. The top right value of this matrix plus the top right value of the second matrix, 8 plus 0, which is 8. The bottom left value of this matrix with the bottom left value of this matrix of the second matrix gives us 8 again. And well, 7 and 2 gives us 9. That is really basic matrix addition. Now, matrix subtraction. It's the same concept as matrix addition. Let's see what's going on here. So you have 1 minus 1, which is 0, 2 minus 3, which is minus 1, 3 minus 5, which is minus 2, and 4 minus 5, which is minus 1. Again, we're using the same methodology as we did for matrix addition. Now, matrix multiplication. This is something really basic. Again, what you have to do is multiply the rows of vector A, of matrix A, with the columns of vector of matrix B, right? So what we would essentially do is, well, let's just say we have, can I annotate? I think I can. One second. All right. Assume you have these two values, and you have these two columns, right? What we do is we multiply 1 with 3 first. That's the first step that we do. And we multiply 7 by 5. So what we get is 1 into 3, which is 3, plus 7 into 5, which is 35. So this value over here would be 38. We do the same thing for this column right here. What we do is 1 into 3, which is 3 again, and 7 into 2, which is 14. So that leaves us with 17. 1 into 3, 7 to 2. Perfect. Now, let's backtrack a little bit. Let's erase this stuff. My apologies. Clear. Drawings. Perfect. Now let's look at the second row of vector of matrix A and these two columns of matrix B. Again. So what we do is multiply 2 by 3 and 3 with 5, 4 with 5, my apologies. So you get 6 into 20, 6 plus 20, which gives us 26. So we can write this as 26. And what we can also do is multiply 2 with 3 again, but with this column, and 4 with 2 again. So what we get is 4 into 2 plus 2 into 3, which gives us 6 plus 8, which is 14. And we can form a completely a new matrix, right? We can form this new matrix, which would have the values of 26, 14, and the two other ones that we found out earlier. Perfect. All right, let's go ahead. Now we look at the transpose of matrix. Now the transpose of matrix is a very basic concept. All you have to do is convert rows into columns, right? So let me annotate that again. You have this row, right? As we can see, if we were to input this matrix and try to find the transpose of it, what we would get is, well, this row is converted into one column. This is our second row, which is converted into the second column. And this is a third row, which is converted into the third column, right? This is really basic. And what this actually helps us do is, if we were dealing with pixel data, then what we would get, if, for example, if this was an image instead of numbers, if we had a matrix input of an image, what we could do is sort of rearrange that image to find different patterns